Wow. Okay, thanks a lot for coming. This is amazing. This means the world to me. Thanks a lot all for coming. So there are lots of great adjectives about you here, but of course the most important adjective about you is that you're a captive audience. The door's closed and will be for almost an hour. So I have you for myself, and I can do what I want. So one thing I could do, and actually that would be the expected thing to do for a professor, is to tell you about my own research. So I could give you a 1-hour talk about algebraic graph algorithms. That's actually a great topic, and it contains stuff like the fast theta transform and the Artin-Wederbach theorem and the Clifford algebra. There are exactly 2 people at ITU who would like this, and one of them is in Switzerland today. So maybe surprisingly, I'm not going to tell you about my own research at all. So what could I do instead? Well, so elderly academics all think they become philosophers, and I could give you my own view on the philosophy of mind, and this would be called What Is It Like to Be Merge Sort? I kid you not. Oh, you're a super grateful audience. Thank you. This is actually, I mean, I'm halfway done with this. This is a realistic threat. I could have done this, and it would have amazing jokes about Mary the color-coding scientist and balancedness as qualia of redback search trees, and this is, well, partly bullshit, but not complete bullshit. This is so if anybody would like this lecture at some later time, please invite me. Instead, so what I chose to do instead is to actually give you the best introduction to algorithms lecture I can think of, and that is born partly out of frustration. So I try to communicate algorithms to the greater world a lot, including to students, the public, and journalists. And 10 years ago or so, when I talked to a journalist about algorithms, the copy you get back from the newspaper invariably autocorrected the word algorithm to logarithm. I kid you not, right? And then I would have to take the phone and say, yeah, you need to change logarithm back to algorithm. I really mean algorithm. And mostly the journalists just said, okay, yeah, if that's important to you, because we will, if you laugh at each of my jokes, we will never get out here in time. Because algorithm and logarithm is just something with math and it's complicated, but okay, they fixed it. So something like 10 years ago, I spent a lot of time evangelizing about these things. You can see here so you can see by the amount of hair that this is some time ago. This is me talking about algorithms for finding partners, so algorithmic love, if you want. Right? And for news filtration and for Netflix and filter bubbles and so on. So I talked about these things in the public many years ago before it was cool. And here you can see something we produced at ITU very early on, very high production values about monks writing and inventing Google. You can see monks being there in the background, inventing Google's algorithm 1,000 years before, and then it's all explained. And we did this for Denmark's Radio some years ago, and I'm pretty proud of these things. This is so I spend a lot of time evangelizing about algorithms actually having an effect on the world, and this was a complete disaster. So I and other people did this because after 2010, algorithm just became something fishy in Google or Facebook that selects our news. Okay, so it turned from logarithm, which was wrong, to the thing on the right, which is also wrong, and they are wrong in different ways. I would like to just be slightly more, most of you to leave the room and being slightly more right about this. Both of them, they're not completely wrong. They're not insane, but they are not how I would define an algorithm. Okay, so that's today's lecture. Algorithms explained. My attempt at the best job to explain what this is I do, from my perspective. Okay, and this is a big story. It goes into 2 parts, and one is just a history of cognition through the civilization, and we start in the Great Rift Valley of Africa 35,000 years ago. The biggest intellectual breakthrough of human history must have been that somebody saw that the day I was worrying about my child being sick, and the day I sort of eat some funny mushrooms, and this day I went out fishing, these 3 days and one more day actually are just 4 days. And the way to count days and the way to count cows, because I could have given a name to these cows, is also just a way of counting to 4. So somebody somewhere must have had this amazing insight that there is a concept called fourness, and 4 counts days just as much as it counts cows. It throws away a lot of information about the days, and the day I was worrying about my child being sick, it was a terrible day, and the cow maybe, so much of the information is thrown away. But this must have happened at some time. It's probably some 25,000 years ago, maybe 35,000 years ago. It's a prehistory, so we don't know. But this was a breakthrough. Right? And this then, so because we moved from a domain-specific concept of quantity, 4 cows, 4 days, to a universal concept of quantity, where we could add 5 and 1 and get 6. And then it took much less time to see that we don't need a separate symbol for 1 and one for 10 and one for 100, which the Romans had, but we could make do with much better symbols. And then it became not only, our concept of quantity became not only universal, it could count anything, but it also became scalable. It doesn't matter whether you add 5 and 1 to get 6, or whether you add 5 and 1, I think these are septillions, to get 6 septillions. Okay, so these are important words here, universal, scalable. I will tell you the same story again now about music. So in the top left corner, you see a stone that explains how a certain melody was to be performed in ancient Greece by explaining how to pluck a specific instrument, a lute. It explains how to tune it and in which order to pluck the strings. We don't have the lute anymore, so we have no bloody idea how this melody sounded. This was a domain-specific way of denoting melody, and it is lost to us today. Somewhat later, medieval Europe did the same thing. Monks had this problem of remembering hundreds and hundreds of different chants, and they invented some kind of notation with squiggles above the words, reminding you whether the melody goes up or down there. This was actually good enough to remember the melody if you had sung it 117 times before. This was a great way of recording it to remember it later, but it was also imperfect. It was highly domain-specific, and frustrated by this, Guido d'Arezzo, 1,000 years ago, invented a system of notation for music that used one way of arranging pitch, so you could see the difference between da and da, and another way of noting lengths, so you could note the difference between da and da. And that was enough. That was all that was needed. It took thousands of years, but that was all that was needed in order for Guido to write down all these chants in a notation that we can read and understand today in a unique fashion. And amazingly, 1,000 years later, Arnold Schoenberg still used, and we are all using today, the same system of notation to write down music that certainly Guido had not thought about. So very deliberately, Arnold Schoenberg used this to write down music that nobody had ever heard before. And by the way, which very few people still want to hear today. But that's not the point. The point is that the notation system, by virtue of being universal, is able to express things you hadn't thought of when you invented the notation system. So the universal notation system allows creativity in a way that the other notation system did not allow. As soon as Guido had this idea, you could write music in several parts, 4, 5, 6-part harmony in the Renaissance, and then the glorious music of Bach, and then it ended in somewhere in the middle of Schoenberg's life. So this is an amazing story. It's the same story I told you about numbers. Now it's about melodies, but it's the same idea. But now I also point to creativity as being an important part of this. Right? Let's do the same thing for concepts or words. Assume Alice wants to talk to Bob, and she wants to tell him the concept of fish. Right? If she is in Mesopotamia or Egypt or China, there will be an established symbol for fish. It's up here. Depending on when you are in Mesopotamia, it's this or that. And the same story is true for all logographic writing systems, that there are symbols for concepts. And if you want to communicate fish to Bob, you just send him the symbol for fish. A completely different way of doing that is to send him use an alphabetic writing system, which, with much fewer letters, can express the same concepts. So a priori now, the logographic writing system, the one that uses symbols, and the alphabetic writing system, the one that uses way fewer symbols, are equally good at communicating fish. Okay? But there is a qualitative difference between these two writing systems, because Alice can also communicate the principled denial of the sacrament of holy orders. Right? She can reject Catholicism. And this is important. She can reject Catholicism in a system of writing that was invented to support Catholicism. right? This is a big deal, right? This is a big deal, that the fact that the system is no longer tied to the domain in which it was invented allows you, by virtue of its universality, to express concepts you didn't have when you invented the system. Same story we told about Guido, now I can tell about Luther. And of course, when I say Luther, we immediately think of the Gutenberg Bible, which is sort of the short version of this entire story, that we had this amazing invention in Europe where some German guy invented movable type. No, he didn't. Movable type was around for hundreds of years in Asia, in Japan, and in Korea. So they had movable type systems for hundreds of years before Gutenberg got the idea, but they didn't have the alphabetic writing system. And if you have to set up a page of writing like this, and your case of symbols is 10,000 large, then you're not winning anything, right? The good idea about movable type loves the smallness, the finiteness of the small alphabet for the universal system of expression. Okay, so to sum this up, information technology, in this case the printing press, and universality and the smallness of the alphabet. When these things come together, you can transmit new ideas with speed. Everybody has access to it. And this leads to unprecedented human flourishing. It led to the Enlightenment and the Industrial Revolution, and the fact that today a random young mother in Africa can look into the eyes of her newborn child and be pretty sure that this child lives until the ripe old age of 75. I kid you not, right? So we have all of that. We also, of course, had the 30 Years' War, right? And unprecedented human misery because of this. Right? So this is an amazing engine of change, and maybe you think that's a good idea or a bad idea, but it's there. This is what it is. Okay, and so this was numbers, so quantities, music, so melodies, and words, concepts. And now we go this next step to processes, to algorithms. So there's a very entertaining tradition in our civilization of expressing processes. Do this, then, and then do that. And here are just 3 examples of this. This is Baroque dance. So the squiggles here on the floor tell you how to move your feet and walk around in the room and dance around your partner. This is a highly specific, domain-specific notation to explain a process. Right? And there are beautiful books that you can read, and all these systems of notations are slightly different, and they are highly focused towards the domain that you want to express process in. Amazing stuff. And another much more accessible to most of us is, of course, recipe books. These have been around also for a very long time. This is one of the oldest manuscripts we still have. The Cooks of King Richard II, a form of curie. This is from the French, cuire, which was the old way, the fancy way of saying cooking in England, because all the fancy words in English are French words. And this just is basically a collection of recipes for food. And maybe most relevant for us, of course, and we have to have this in a lecture about algorithms, the compendious book of calculation by completion and balancing by the Persian mathematician Al-Khwarizmi, who gave his name to the field we're in. So algorithm is a Latinization of Al-Khwarizmi's name. And this is a book that is just filled with algorithms that operate on numbers. This is a book that is filled with algorithms that operate on food. And this is a book that is filled with algorithms that operate on, I don't know, human bodies, feet. Okay, and let's look at the one in the middle just a bit more. So here's an algorithm. It's just a domain-specific algorithm, so it's not quite the thing I study. But it contains all the things that are important for us. There is some kind of output. We want to make curry the Indian way. And there is input, in this case 2 small chickens and onions. And there are parts where it says do this first and then do something else. So there's a description of the process in the order in which it has to be executed. And then there is what today a programmer would call a while loop. Fry them together till they are brown. So there's repetition of action until a condition is fulfilled. And that is all you need. So if you've never seen an algorithm before, this is the best way. So thinking of algorithms as just being recipes, but not only about food. Okay, so algorithms are recipes, but not only about food, is a way better thing than thinking about algorithms as logarithms or black boxes. Okay, and this is huge. That would be a huge process, right? If just everybody understood this much about algorithms, this would be huge. Because recipes are not black boxes, for instance. I'm sure there are many jokes here, but since you laugh so much, okay. So famously here is then the Industrial Revolution comes, and people start to build calculation machines, and this is famously the note G of Ada Lovelace's translation of an Italian mathematician's instruction manual to Charles Babbage's Analytical Engine. And here Lovelace, the Countess of Lovelace, wrote down the instructions step by step for computing something very nerdy, the Bernoulli numbers. So this is an early example of a highly precise description of an algorithm in math. This operates on numbers and doesn't want to do anything else than just find a specific value for something that we don't know a closed formula for. Still, this is a breakthrough. This is a huge thing. The machine was never built, but there is an instruction manual for writing programs for the machine. And this is what we see a page of here. It's remarkable because Countess Lovelace started thinking about what these things could lead to, and this is basically why we're here. So here she is as a much younger girl, but I think this is a beautiful picture, because there's a famous note of her that says, the analytical engine, this is the machine she wrote algorithms for, the analytical engine might act upon other things beside number. Okay? And let's just take that quote in full. It's slightly boring, but I will read it aloud. The analytical engine might act upon other things beside number, where objects found whose mutual fundamental relations could be expressed by those of the abstract signs of operations. This is what people today would call algorithms, and which should be also susceptible of adaptations to the action of operating notation and mechanism of the engine. Supposing, for instance, and outcomes, supposing, for instance, that the fundamental relation of pitched sounds in the science of harmony and of musical composition were susceptible of such expression and adaptations, then the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. This is the conceptual breakthrough. Understanding that you can use this growing body of very precise algorithmic processes on something else than just doing computing the Bernoulli numbers. So Ada had this observation in 1842. And then it took a long time in math before math caught up with this. It required logic to move from philosophy and language to math. So it required logic to become a piece of math. That took 2 generations. Frege, Boole, and so on. Hilbert, and then and Gödel. And then in 1938, finally, Alan Turing writes down something that is completely obvious to us, namely the universal machine, which today we call the Turing machine. So the idea of writing down a machine that could do what Ada envisioned here, that is the breakthrough paper of Alan Turing from 1938. And then it took no time for John von Neumann to build the bloody thing, and today it's here and there, and it's in everybody's pocket. So this is a huge thing. This is the breakthrough technologically. And today we are living in Ada Lovelace's dream. We have transformed the entire world into bits and bytes and feed these into analytical engines. Right? This is the dream. Okay. So to sum this up, this ends the first part of the lecture. To sum this up, the algorithms are processes or methods or recipes. You can find any word you want up here. All of these 3 words are good, I think. So that are universal. Let me talk through these 3 things. They are universal because they are domain independent. And by virtue of being domain independent, they allow new ideas to be formed, thereby enabling creativity. They have infinite reach because by being domain independent, the solutions to problems can be transferred from one domain to the other. And they are disembodied. Okay. They are also finite, like the English alphabet. They use very few instructions that are very powerful, and thereby they can be transmitted. They can be scaled. They are lovely for digital technology. Digital technology just wanted this concept and then it exploded, and they are universally accessible. Right? Everybody today has a piano in their pocket. Everybody today can produce films. Right? This is an explosion. This is a democratization of the creative process by virtue of the accessibility that comes out of of the finiteness and the universality. And this becomes then the most important part of the lecture very soon. They are legible. Readable is a good other word for that, lesbar. They are legible, so they are seen, they can be made explicit, they can be explained. That's my job. When I succeed, they are even understood. Once they're understood, they can be improved. That's my job as a researcher. So here, this is me as a teacher, this is me as a researcher, simplified. And I explained all these words except for criticized. So I will explain that in something like 25 minutes. So the word criticized so far is a question mark. So these were the virtues of algorithms. On the next slide, I have the sins of algorithms. Any guesses? They are, of course, exactly the same. Right? So I'm not tone deaf to this, but I will get back to it. But let's take the value part a bit more important. Because there's still a lot of misunderstandings about what algorithms researchers do and want and think. And I made an exercise to myself to explain this. And I want to focus on these 6 values. The 3 first ones are the most important. These are the core values of algorithms theory. I think every algorithms theorist in the room shares these values with me. The other ones are much more modern, and the last one is really a newcomer, which has just been around for a few years. Okay, so the most important parts are the first 3. And also as an exercise to myself, I want to do it by a running example. Right? I just want to explain all of this with the same algorithmic problem. And it's a super simple one, namely finding the maximum. And you can all see the maximum, and actually Philipp Bille is in the room, so it's super easy problem because it's right there, right? The maximum is visible to all of us. And this is because this slide sort of makes it deliberately too easy for your brain, because your brain is this parallel processing engine and your eyes help, that you can all see the maximum immediately. This took you no time. Right? In reality, of course, there are many, many more numbers than 8, right? And you can't see all of them you can only see one of them at a time, right? Okay, so I translated the problem to this. There are 8 numbers on behind these pieces of paper, right? And we can't see them at the same time. So this is my way of trying to make this analog. An analog version of this problem is on the blackboard. Okay. And here is our algorithm for finding the maximum, and the way we would normally express it. We express it in very precise prose, precise enough that I could actually confidently ask anybody on the first row to execute this algorithm and get the right answer. I will do it myself so as not to embarrass anybody. So this will slow down now. If you have seen an algorithm before, this will be intellectually insulting to you, if really, right? Because you know how this works. If you haven't seen it, this is your first algorithm. Okay, I want to find the maximum of these numbers. I will tentatively assign a new value, m, to negative infinity, just to make sure that that's not going to win, and then process the numbers from left to right, replacing m with the current number. Okay, so what I mean by this is that I go through them from left to right. I brought this red marker to remember where I am. I'm really a computer, I'm just pretending. So, replacing m with the current number if that is larger. Okay, so I look at the current number. 48 is certainly larger than minus infinity. So I'm following the instruction and therefore replacing this with 48. And 84. Thank you. Okay, and probably finally return m. Do I have to do this now? Okay, so normally we don't express these things in prose. We express them in slightly more stringent notation. I looked ahead, so I know what is on that slide. So I know what to do now. I have to repeat, then process the numbers from right to left. So what this means to me is that I should now look at the next one. Compare this value to m. It is not larger, so I'm not doing anything. Okay, this very quickly becomes boring. But 8 is exactly the right value scientific. Oh, this is way larger. 454. It will get harder in a moment, but we will do this slowly. 454. Right? I need some kind of memory in order to know how far I progressed. This one is smaller. This is harder. No, still smaller. Each of these is a mini computation I have to do in my brain, right? But I can do this. Actually, I'm aggressively using the fact that I understand positional notation, so I only have to look at the leftmost letter. Many things are going on here. If this were Roman numerals, it would be much harder, right? This is close, but 6. Okay. And I'm out of numbers, so what should I do now? Finally return m. So m is 554. Ta-da! Right? Okay. So this prose was almost good enough to certainly that I could communicate to myself 1 hour later what I was supposed to do. And normally we express this in some more precision. So for instance, the role played by this red dot, I sort of cheated because it just said process from left to right. If you want to actually be very precise, then you have to instantialize the red dot as some kind of value that proceeds from I, and then a lot of time it's going to be increased by 1. So after 1 it's 2, and then it's 3, and so on, until it's 8, and then we drop out of this so-called while loop. Okay, so the details are not important. Take on face value that there is a way to make very precise what I mean by do this until that, and how I can formalize the function of the red dot. Right? So here it is expressed in pseudocode. This is still used to communicate from one human to another human, but this is so precise that I can even translate it into a concrete programming language. Here it's Python. And now it's so precise that I can put it into a computer, and the computer will do exactly what I want it to do. Okay, so the step from the very precise prose to the programming language is a banality. Right? The students my students in the room should be able to get from the top part to the bottom left part without any problems. Okay, so this was an algorithm. And this is enough to hammer home the first point. So our requirements to clarity are extreme. Okay, so algorithm researchers take up an extreme position on comprehensibility. Right? We want to express our algorithms in an unambiguous, explicit, legible way, lesbar, readable, which is intentional and crisp. It should be short and sweet. This is what we want. The programming languages we use, for instance, have entire books devoted to what does a comma mean in this programming language. We want to be extremely precise. And this, you may think, is a trivial statement, but I promise you it is not. Many people think exactly the opposite of us. Right? Many people actually think that what we do are machine-learned black box operations that inherit statistical patterns from learned data. Some people are doing this, and they also do algorithms in some fashion. But people like me are not. Algorithms researchers are very devoted, and computer scientists in general are extremely devoted to the first value here, clarity in expression. We want to communicate the process in an unambiguous way, so as to be readable and executable. Okay, this was the first point, and believe me, I mean, this was non-trivial, and most people misunderstand this. Not you, because you're beautiful and lovely and intelligent and so on. Correctness. So here's my pseudocode, just because it's typographically the most pleasing way of representing the algorithm. If you don't know this, then it may come as a surprise to you that when a computer scientist sees this, then he or she will try to infer from a minimal logical assumption, namely that true is true, the correctness of the code. And depending on where you took your computer science education, we do this by decorating this program, either explicitly or implicitly, by lots of logical expressions. Each of these steps is tiny, and for instance, so there is there's a rule that says that after I have assigned the number 1 to the variable I, then after that I can safely assume that I holds the value 1. Right? And I can see people starting to look really tired now. And I promise you, this is super duper boring. Right? But still, this is what we're doing. Right? This is the extreme form of proving correctness of programs. Right? But even weaker forms of that, so when I communicate an algorithm to students, there is always a proof of why it works. There's a formal piece of math. So we have this routine of not only communicating the algorithm, but also communicating the entire reason for why this algorithm works in the most stringent form of explanation known to mankind, namely math. Okay? So we take an extreme position on correctness in the sense that we use formal logic in the tradition of Leibniz, Frege, Hilbert, Russell, and we are rigorous even by mathematical standards in establishing our correctness arguments. We are way more rigorous than theoretical physicists, for instance. Everything we do has a mathematical proof. So we are logical positivists. We are not empiricists. And again, I don't think this is clear to most people, but this is really what we are. So we don't do empirical verification of our algorithms. We don't test them in the wild and see what happens. We prove their properties as a piece of math. And finally, and this is where I come in, my research is in efficient algorithms. This is the value I care most about. So how fast is this? Well, you saw this on the blackboard. It was, 120 seconds. But that's not what we do. We don't run them. Instead, we count operations. For instance, we could count how many assignments are there in there. There's this assignment and that assignment. And this will be executed n times. Right? I starts with 1. It's counted up by 1. It does that until it reaches n. So we go through this n times. So there will be this comparison. And in total, there will be 2 n comparisons. Right? And then we throw away the details and just say that the number of operations is linear in n in the worst case. This is our way of understanding how this algorithm works. We just want a functional, we want to write down the functional relationship between the number of operations of this thing and the size of the problem it has to handle. This is what we do. And again, this could be a surprise. Right? We're not, I mean, this is, very few other sciences do this. So our analysis is a piece of math. It's not a piece of empirical analysis. Right? We don't run it on some data and look on the clock. This is interestingly not what we do. I know this, but many people may not. Let me do this. So this was really a toy example, which doesn't allow me all the things I want to say. Let me take a richer example. Now I want to find not just the largest number. I want to find the largest 25% of numbers. And the largest 25% when there are 8 numbers are the largest 2 numbers. So this is an incremental improvement for us. So in this case, the largest 2 numbers is, if I did my math correctly, this. Okay. And how could we do that? Suggestions? Now you have to say something. So I wanted to find the maximum. Sorry, I explained to you how to find one maximum. Now I want to find n over 4 maxima. And of course, I can do that just by repeating this algorithm n over 4 times. Right? So let's do this really quickly. Let me cheat. I actually remember that. So I ran it once. Boom, that found me this value. It was here, right? No, it was here. Right? So great, that is the largest number. Now I have to take this out or something. I guess I can replace it by minus infinity. So take this out, replace it by minus infinity, and then run the algorithm again. Oh, remember it? 4, 5, 4. Run the algorithm again, find the next largest number, which, can somebody help me? Was it here? Yeah, probably this guy, right? I'm cheating here, but you could do something like this. Just run it a couple of times. And this actually works, but it's already much harder to write down. Right, here's the code of what I just told you. It's still clear what's supposed to be doing, what's supposed to be going on. It's not, the correctness proof of this is just terrible. I tried just to impress you, and I failed. What is the running time of this? Now, this is a question to my first-year algorithm students. What is the running time of this code? Oh, I could ask the Weisstein as well, but somebody has to say it. Yeah, quadratic, right? Because so if you have taken an algorithms class, you will immediately see there are 2 nested for loops. The inner one runs for n operations. The outer one repeats the inner one n times. So this entire thing will run in time n squared. And this is how we analyze algorithms. And now comes the point. This is the hardest part of the lecture. Now comes the point. What could we do instead? Is this the best way of finding the n/4 largest elements in A? Yeah? Yes, excellent. Okay, so we could start by doing this instead, and then it's completely clear where the largest ones are. Right? And so compare these two approaches now. Our improved algorithm is clearer, it is obviously correct, it actually is faster because sorting is extremely well understood and there are fast algorithms for it. And it works basically because there's a growing body of algorithmic problems that we have understood very well over the last 2 generations that we can build on. Okay? This tells you everything that we care about. Right? The same problem is now being solved in a way that is easier to understand and faster and obviously correct. We love this. Right? This is great, and it is part of the scientific story because it builds a growing body of knowledge. Right? All the hard part of the argument are in here, and that's already been done, and I taught you about it. Yeah. Right. Okay. Awesome. So these were the core values. If you fall asleep now, that's great. Right? Now come funkier stuff. So and I claim that all algorithms people agree on this. Now come funkier stuff, which is more modern because I can put other words on here which are maybe surprising to you. One of them is privacy. So I showed you how to get from some inputs to finding the maximum. We've seen this algorithm now 1,000 times, no, 3 times. Right? It solved too much in some sense, right? Not only it found the maximum, but it also found all the other values, and it found out who had the maximum. Is this necessary? Can we do this instead? To the left, just finding who held the maximum without learning any of those values? Or can we, to the right, just find the number without knowing who had the number or any other numbers? This is also a question of finding a maximum, but it is much more careful about not revealing other parts of the computation. Right? And there's now an entire discipline devoted to doing these things, and this is new and fresh, and this was unknown in the 40s, 50s, and 60s. Now this is an important core part of algorithmic problem solving, to solve exactly the problem you wanted to solve, and nothing more. Right? And some people in the room, actually, this is their research agenda. It's not mine, but there are extremely strong people in the room who do exactly this. Right? I can show you a toy version of it, sort of baby crypto. I can show you how to get from here to there. So this still finds the maximum number. It also finds all the other numbers, but it doesn't know who had which numbers. That's not quite, it's still too much information, but I can show you how to do this. Right? And it's just a simple modification of this algorithm, which we now have seen 5 times. So what should we do? We start by shuffling the input. Okay, take the input, shuffle it. This can be done. Ask some of the people in the room who just nodded now, right? And then run the standard maximum algorithm, right? Then you find the maximum. You just had no idea who had it, and maybe that's what you wanted. Okay? It hasn't become more correct or faster or easier to understand, but it now achieved a different new value, namely privacy. The coolest part here is truth, so that's also hard to understand. Yeah, let's do this because it's fun. Okay, so this was privacy, and this is new and fresh, and I don't do any work on that. The next part I also don't do any work on. I want to sell this banana to the highest bidder. And here are 8 people, and they all know what the banana is worth to them. We are in economics now. People have agents, have private valuations of a good they want to have. Some people, like Don, would happily pay 454 kroners for the banana. Other people, like Hans, doesn't really care about the banana. So he would take it for 3 kroners, but no more. Okay? So each of those would be happy to make this deal for the price given here, but no more. That's the maximum valuation they would want to pay. That's the game. That's the standard economics way of understanding transactions between humans. If this offends you, think of this as a public good, like access to healthcare, and think of this as need. Right? That people could be in different states of actually requiring a new liver, right? And we want to give it to the person who needs it the most. It's the same problem. I just framed it differently now, and some people may take it more seriously then. But let's go back to the sell a banana to the highest bidder. So this is a public goods game where I have something to sell, and I want it to give to the person who needs it the most or is able to pay most, wants to pay most. Now, I want to auction this off. And now imagine we are in a world where, and I want to do it in a sealed bid. So the idea is that each of these 8 people writes their valuation on a piece of paper and gives me that valuation on a piece of paper, and then I find the maximum and give them the banana. A sealed bid auction. This is done all the time in politics, in housing, and so on. The problem with this process is that Don is not incentivized to tell me his maximum value. Put yourself in the shoes of Don. What should Don write on his piece of paper? Right? He's not going to write anything larger than 454 because that would not be a good deal for him. But I mean, if Don could get the banana for 400, that would be great for Don, right? So Don would actually like to misrepresent his array, his value. He would like to announce a value that is smaller than his true value. And they all want to do that. Everybody of these eight people wants to misrepresent their value. So I still want to solve the maximum problem, but now I'm on a computer where the cells in my array are disincentivized to tell me their true value. It's a really weird variation on the von Neumann model. Right? They may tell me this, and then I would give the money maybe to Alice, right? Who gets it cheaper, but I didn't make as much money as I could have made, and Don didn't get the thing, and this, depending on which context you're in, may be socially suboptimal. Amazingly, this can be solved. This is not important. And the solution is this. I will announce that I will sell the banana to the highest bidder for the second highest price. So I just announced, please give me your bids. I will read them, and then I will give the banana to the highest bidder for the second highest price. So in this case, Don would get the banana for 312 kroners. Think about this over a beer. Maybe play it out with 7 friends if you have 7 friends, but after the beer you will. This means that put yourself in the shoes of Don. Don might as well tell me the truth, right? Because he's going to get it for Alice's price anyway. He doesn't want to underbid Alice anyway, because then Alice gets the banana. And he's never going to pay more than Alice's valuation. Another maximum problem. Now I can incentivize the array to tell me its values. Okay. And finally, the newest one, fairness. We could have time for questions, or we could talk about fairness. But of course, we want to talk about fairness. Okay. Let's get back to the maximum quartile problem. I wanted to find the 2 largest numbers in this array. Right? And we all did this several times now, 312 and 454. We are still friends. We will not be in 60 seconds. Okay, the fun part is over. Because what are the maximum numbers in this array? So now I did what I tried to avoid for 50 minutes. Now I contextualized this problem and made it very clear that this is a decision that's going to affect those people. Because the score could be, I don't know, the credit score or the score on a test that I will use to make a decision about these people. And it's not at all clear what the right answer is here now. Right? Note that, for instance, Claire, Erica, and Gitte did amazingly well, right? But none of them has the highest number. So everybody in this room knows exactly what the correct, morally, politically, ideologically correct answer to my question is. You also all are sure that everybody who thinks different than you has some kind of moral defect. And I promise you, you all have different opinions on this. Right? This is a toxic question of the highest order that cuts right to the quick of where it hurts. Right? And we still have to sing together in a minute, have cake together, and have a beer together. Right? And we need to be able to talk about these things very, very soon. Because I can make this even more toxic by putting here the name of 2 Jews and 6 Germans. Okay? This becomes as hard and painful as you want. Right? Again, everybody, I know exactly what the 2 numbers are that I like here. And I'm sure everybody in this room, many of you will think something else. Right? I'm not telling you. So what I sold as a toy problem, which had some kind of pedagogical value so I could tell you about algorithms and be excited about it, it wasn't a toy problem at all. This is the hardest problem we have. We have some individuals that will go through this machine. They will be turned into bits and bytes, go through this decision-making process, and then based on that decision-making process, they will get a job or get a grant or go to jail or get insurance or be shown the ad for diapers or get admitted to ITU based on exactly this kind of process. This is a highly contextualized problem that has real effects on these 3 circles here. And you can make the problem even more toxic and harder by viewing these 3 circles as samples from different distributions. And you can start discussing what should it mean that the red distribution has a mean that is slightly to the right, but the green distribution has a slightly higher tail. Are the 2 green dots more alike, or are the 2 vertical dots more alike? All these questions are core questions that appeal to fundamental assumptions we have about what the good society is. And the answers to all these questions have an effect on these algorithms, how we write them. Okay? I told you we would stop being friends, and we are. Can you feel how much colder the auditorium is getting? Right? Because, so I hope I gave this presentation in a way that some of you found completely unpleasant for the entire time, because can't he hear himself? And this is all terrible, right? Algorithms make decisions. Society never had these problems before. I'm telling you about the triumphs of an approach to problem solving that is completely alien to many people, including me. Right? This is just simply not, we don't like this. Because all these problems we see today, the problems I told you about for Google and Facebook, which I showed you lectures about 10 years ago, we never had these problems before. Right? So back to the wrong understanding of algorithms, that was that algorithms are something in Google and Facebook that selects our news. I made fun of that, but there's actually no reason to make fun of it. This is actually a pretty valid way of understanding algorithms. But sometimes they actually make better decisions. And most importantly, and this is the point of this entire lecture, people suddenly care about news curation. The processes that select news, right, people like Dewey or Chomsky have written good books about it to a very, very small audience, suddenly everybody cares. And that is a good thing. Because the problem is not new at all. There was always something that made the decision about who gets the job or who gets a date with Alice or who gets the loan or who pays full price for that thing. The only new thing is that we've made this something legible and therefore subject to criticism. Okay? So this ends, I promised you there was amateur philosophy in here, and we are finally here, right? This explains algorithms very strongly as part of the open society that makes processes visible and therefore subject to criticism. It's also creative and fun, and we can solve problems and we can communicate, and it democratizes creativity. It democratizes access to information and all these things. All of this is true and great, and you can read about that everywhere. But by virtue of turning these problems into something that is readable, we can also suddenly think about them. And so, because, let me end with 2 proper quotes on one page. All life is problem solving in search of a better world. And for this, we need to understand what we're doing with algorithms. Thank you very much.